Please welcome Daryus Chandra.
So tonight the topic is what is quantum internet. So it's pretty straightforward question. If you already know the answer, I don't think you should be here because. So I don't think. So if you are in a hurry and expect a definite answer to this question, you will not get it, because in here I try to convey you what is like. If people talk about quantum internet, what is exactly what they mean? What is the goal of it? And what is like, I also want to explain to you what is the challenge before we can get the so-called quantum internet. So yeah, so my name is Daryus Chandra. I'm a PhD researcher with School of Electronics and Computer Science. So researcher is a word that we use if we don't talk to retailers, because if we talk to retailers, we say PhD students, because we got discount for students. But if I talk with my parents, I will say I'm a researcher. It's kind of weird situation. So I also a course instructor with lifelong learning department. So currently the lifelong learning department of University of Southampton try to push a different kind of lifelong learning course, because currently, like previously, they always have the language learning course, creative writing course, and that stuff online and that kind of stuff. But now they kind of try to promote different type of course. One of them is the introduction to quantum computing and quantum communication, but for public. So it was interesting. If you want to enroll like a full time to understand what is quantum computing and quantum communication, please check the lifelong learning department website at the University of Southampton. So, how many of you have read something about quantum on the news? Because currently, like, the news about quantum is basically everywhere. It doesn't have to be in the like science articles. It already in like BBC or The Guardian. It's already in the mainstream media. So we know that, like for example, UK already invest like 250 million pounds to invest in a quantum technology. So I think this is one, like as a public engagement, as a taxpayer, you have the right to know what is the money going to. Like it's such a huge amount of money.
What is this one?
So we also, I think this one is right. Also, you may also see like there is a news about China's quantum satellite. So probably we, like in the Cold War period, we have the satellite race between the two countries. Now we kind of entering the new era. It's like the quantum race, because now all of the countries invest a lot of money in this quantum technology. So yeah, we have, so for example, Beijing and Vienna have a quantum conversation. Like, what is a quantum conversation? And then China's quantum satellite. So what is quantum satellite? So also, it is pretty serious, because President Trump has signed 1.2 billion law to boost US quantum technology. So President Trump already signed a 1.2 billion pledge, 1.2 billion US dollar for quantum technology. So people already noticed that this is such like a very important milestone in science. So you somehow have to invest a lot of money, a lot of effort in this quest. So now we have quantum technology. Now the quantum is so high, people just connecting like all technology together. We have internet and we have the word quantum. Boom, we have quantum internet. And now people have blockchain technology, we have quantum technology, and then people say, why don't we have quantum blockchain? And we have deep learning technology, and we have quantum technology, and why don't we have quantum deep learning? And then we have video call technology. Why don't we have quantum video call as well? So a lot of things, they just connecting because the word quantum is so hard, and then they try to find what kind of technology that we can connect together, and it sounds so like serious, sounds so hard. So this is the inside joke with us. Is it quantum superposition or is it just quantum superstation? Because some of them doesn't actually make sense to make quantum because, like, why? Because we can see throughout this lecture, like, what potentially can be used as quantum and what is not probably, because you have to differentiate when media try to sell you something like quantum blockchain. Like, is it really quantum blockchain? Is it, or is there something they try to hide? For example, if someone told you quantum video call, I can make sure to you that the video call itself is normal video call. The only quantum in the quantum video call is only the key exchange. Like the key to encrypt your message is quantum. So that's it. It's basically for us, for scientists, the correct term should be quantum aided video call. It's not necessarily quantum video call. So yeah, people try to sell you something, try to give you like some of that, like a big words, like try to impress you, but sometimes they try to gloss over things. So yeah, in general, when people talk about quantum technology, we can like kind of, because it's technology, you can kind of break down it to smaller categories. So this is my own opinion about categorizing, because there is no formal consensus of trying to group things. So for example, we have quantum communication, we have quantum computing, we have quantum metrology, and we have quantum control, and potentially many more. So in this particular night, a very special night, we will talk only two aspects, because when we talk about quantum internet, there are two main components of the internet. It's the computers and also the communication link. So when we talk about quantum internet, so that's it. It's basically just a combination between quantum computers and quantum communication. But now I want to try to, so my goal is, it's a bit broad theme. I not try to delve so deep in one topic. I try to cover everything as I could. So now, what is quantum internet? Before we talk about quantum internet, but first, let's start with the classical internet, the internet that we currently have. So the day is 29th October 1969. It was a silent night. It was 10 p.m. in the evening, and something remarkable was about to happen. Does anyone have any idea what is going to happen in this particular time?
I think it was DARPA invented the internet, didn't it?
Almost.
Deliveroo stuff.
It's not my birthday. Or is it? So, any idea?
First email.
Yes, almost there. Yes.
Somebody switched on a packet switch network.
Not quite, but almost there. So this is the day of the first message being sent over computer networks. So let me tell you the story. It's a very popular story among computer scientists. So probably you have seen it. So it's indeed the DARPA network they use, the Defense and Research something in the States. So it's between two people named Charlie Klein and Bill Duval, one in University of California, Los Angeles, and one in Stanford Research Institute. So they want to send a message through computer networks. So they already have two computers and they want to send a message using two computers that connected from East Coast and the West Coast, I think. Yes. Where is Stanford?
California.
It's near? Okay, I don't know. So anyway, so they want to send a message between each other. Both of them agree that the message that Charlie wants to send is the word login. Login, login. So they use the computers and also they use the telephone to make sure that the message is actually being sent. So Charlie typed L. So on the phone he said, "Do you see the L?" "Yes, I see the L." And then type, "Now, do you see the O?" "Yes, I see the O." And then when Charlie tried to type the third letter, I'm typing J now and send. And by that, the whole system was crashed. So when Charlie typed the G and sent it to to computer network, the whole system was crashed. So, but 1 hour later after that, they finally managed to build again the system and send the word login successfully. So since 2005, 29 October is celebrated as the International Internet Day. So I want to show you how hard it was to send the word login. It's a simple word, it's just 5-letter words across the computer networks. In my head, the word quantum always appears. So yeah, imagine it's approximately 50 years ago. If you see, like 2019 is like exactly 50 years. So now it's like internet 50 years ago. Now what we have internet nowadays, something like this.
Yeah.
Aww. So yeah, also this. So I believe if you ask 2 people, Charlie and Bill, do you have have you imagined that your internet will be used to exchange cat pictures? Like in the future, 50 years from now. I never met them, probably you will say, I don't think so. Because internet, what we have now is basically create a demand that previously we cannot think about. It's a new demand, like you can exchange cat pictures. Who think that cat pictures is such an essential thing in the world? No one think of it. So yeah, of course internet has like a bad side, like the dark side of the internet, but now try to focus at the happy place, like the cat pictures. So yeah. So in general, like I say, classical internet basically classical computer plus classical communication and some other components. So quantum internet, simply quantum computer and quantum communications mixed together with some other components. The question is now, why? Why people want to connect these 2 together, like what we have in the current internet? So yeah, let's try to demystify these things together. So, what is the better way to start a talk with porn? So, the first is by Jennifer and Peter Shore. Please remember the name, Peter Shore. He is kind of important in this talk. So, in 1998, there is a poetry competition for scientists. It's a thing. He submitted this poem. It didn't win. So, but it's kind of like legendary poem because it's Peter Shore. We will see later. If computers that you build are quantum, then spies of all factions will want them. Our codes will all fail and they will read our email. Till we have crypto that is quantum and quantum. So this was published in a magazine, and then in the same year, in a conference, we have Volker Strassen. It's a German mathematician. Reply to this poem. So see, scientists have a sense of humor. To read our email, how many of the spies and their quantum machine be comforted though they do not yet know how to factorize 12 or 15. So it gives us the idea of what is the progress of the quantum technology actually. It is written in 1998, but unfortunately it's kind of still true until today. given the progress of quantum computers that we currently have. So there are so many ways to approach what is quantum technology, but I'll give you the easiest, like the most common way to approach why we should have quantum computers. So quantum internet consists of two parts, quantum computers and quantum communications. Now we talk the first part first, quantum computers. So we have the Moore's law. This is not actually a law, it's basically just an observation, but people sell it as a law. So from the 1970 until 2016, we can plot this kind of curve where the horizontal axis is the year and then the vertical axis is the number of transistors inside your integrated chip, basically inside your phone, inside your computers. So based on this observation, we basically double the numbers of transistors within the integrated circuits every 2 years. That's amazing. Like, initially, we don't think that's amazing because it's 100 to 200, 200 to 400, 400 to 800. But after some years, it's very remarkable because we kind of reach number that we have 20 billions of transistors inside our phones, inside our computers. Now, the problem is we shrink the size while maintaining the overall size of the integrated circuits. Because here's the thing, your transistor number is increasing, but your laptop doesn't increase in size. It only means one thing, you increase your component. So you shrink it further, further, and further. But we all know nothing can be shrink infinitely. There is a limit of it. And the limit is the particle. So what will happen when you have transistor that you cannot shrink it further? So do you have like a single atom transistor? Yes, there's a thing. Now the question, what is after the single atom transistor? You will slice it into two and we have quarks. I don't even know if you can do something with quarks, but there is a limit. It's the particle limit. So to give you an idea how small is our transistor is, so the most common transistor, it's around 2016 or 17, the most common transistor is 14 nanometers. So to give you an idea how small is 14 nanometers, I have HIV virus next to it. So your transistor, our transistor is smaller than HIV virus. Transistor is the smallest component in our phone. So yeah. So now if I put it next to red blood cell, can you see the transistors? Yeah, we can see it, but as a dot. I can see it, but okay. So it's just a dot there. So our progress in technology is amazing that we can shrink our electronic component into a very, very small size. So the question is, what is happening if we try to push it further and further? So the answer is, the quantum effect starts to prevail. Why does it matter though? Why does it matter to the rule, like to the way we create our computers now? Why? So first, we have the double slit experiment. I will not go through, like deeply explain what is double slit experiment, but it's a demonstration that particle can behave as a wave. So if, like initially when we don't have quantum physics, we always assume that atom is like a billiard ball. It's solid, it acts like a, if you shoot an atom through a double slit, it will act like something solid, act like a bullet. So what you expect on the screen here is just two straight. So that's our initial thought. Because we have the idea that particle like electron, like photon behave like a billiard ball, like something that solids, that behave like a mechanics that we see in our macroscopic world. But turns out when they actually perform the experiment, what they catch in the screen behind is not two strips. It's a multiple strips. It's an interference pattern. the only way to explain this phenomenon is assuming that particle behave like a wave that I show below here. Now, it's not just a wave, but a wave that went through the both slit at the same time. It doesn't make any sense, but it happens. Because what? Because if you don't know, if you just keep it like this, the interference pattern will emerge. But the funny thing is, when you put a camera here on the one of the slit, like you know where it goes, the interference pattern gone. Somehow the electron knew that they are being observed, so they behave like a normal particle. But when you put out the observer in one of the slit, like just you don't know which slit it goes through, the interference pattern emerges. So basically what the electron wants to say is, I went through both slits at the same time, and you don't need to know which slits I went through. If you try to observe me, I come back to my classical property, and then you will not see interference pattern. So just deal with it. Like, I'm a wave, and I went through both slits together, and you don't know which one, it's your problem, not my problem. So that's the interesting part. That particle behave like a wave, not just a wave, but a wave that have this type of being at two places at the same time. So that's first. Oh, that's long. The second one is quantum tunneling. So I said that we have transistor. Transistor is basically like a light switch, because we work in a binary. Our computers work in binary world. It works in a world where it's 0 and 1. You can see the transistor like a light switch. When there is no current, it's 0. When there is a current, it's 1. But the size is so small. And then because if you can do addition in binary, you can do multiplication in binary. If you can do multiplication in binary, you can do exponentiation. If you can do exponentiation, you can do anything. So we work in binary world. So in order to do that, we need a switch. We need something that can stop the particle and say, please stop, don't went through this barrier. Because of the particle and a very microscopic world, in around 5 nanometer, when we reach this level 5 nanometer, the particle behave like a wave. So when you say like electron, please stop, don't went through, because the state of the transistor now is 0. No electron should pass. So stop. But at 5 nanometer, the electron choose to behave like a wave. When he behaves like a wave, he can just propagate to the barrier like a wave. Like you have a wave and you put barrier, the wave can just passing by. So yeah, the transistor that we currently know will not work when facing a particle that behaves like a wave. So it just fails. Your current transistor will not work when it reaches this level, 5 nanometer, approximately. So yeah. So there is no way telling the electron to stop. Well, the electron can choose to behave like a particle or a wave up to them. So it just doesn't work. It will fail. Because the general rule of thumb of building computers now doesn't work. And the third one, photoelectric effects. So the double slit experiments say that particle is a wave. Photoelectric effects say that wave is a particle. This is the theory that gave Einstein the Nobel Prize. So in contrary to popular belief, Einstein never get Nobel Prize because of relativity. Einstein get the Nobel Prize for photoelectric effect. So he showed that light. So when we think about light, we think that light is a wave. But when we perform this, when we shine a plate full of electrons, turns out some of the electron can be knocked out by the wave, by the light. So it means somehow, if light is a wave, this phenomenon shouldn't happen. But the thing is, now it happens. So it means that particle is a wave, but also the other way around. Light as we know it, if we think light is a wave is also a particle. So now, everybody confused? No? No, that's fine. Like all people say, like Richard Feynman said, like nobody actually understands quantum physics, so that's fine. So now we know that exploiting, so we are doomed. We cannot shrink our transistor further because we face our quantum effects. Can we find a way around this? Like these all weird or strange properties of quantum mechanics, can we use it for our advantage instead of like messing around our idea of classical words? How if we can use these quantum properties for our advantage? The answer is yes. The first idea of using quantum phenomenon to create computing machine is proposed by Richard Feynman in 1982. Basically, what he tried to propose is use the strangeness properties of quantum mechanics to simulate quantum particles itself. So he initially think just use it for quantum physics. And then later in 1985, a researcher from Oxford, Robert Deutsch, sorry if I butchered his name, he showed that, well, it's not just for quantum physics. Turns out there is a huge consequences later outside quantum physics. We will see later. So for example, so now since we have quantum world, everything that we know, we call it classical. So now, if I say something classical, it means everything that we have now. This is classical computer, this is classical phone, this is classical bit. So information that we know, that we use to process information, process computation, that we use in our phone, that we use in our computer, is using classical bit, 0 and 1. They cannot be both. They have to choose either be 0 or be 1. But in quantum in quantum world, where everything is strange, everything is weird, this is weird that actually quantum information or quantum bit, qubit, quantum bit, can be used to represent 0 and 1 at the same time. It doesn't make any sense, but it happens. For example, photon, it's the easiest way to simulate. When you have a photon, you know that photon can have vertical polarization and also the horizontal polarization. I'm dancing. But we also know that we have the diagonal polarization. So in some sense, a diagonal polarization, it's in between state of vertical polarization and horizontal polarization. So in a way, photon in diagonal polarization is kind of in a superposition 0 and 1. It's just a matter of we put name to horizontal as 0 and vertical as 1. But we can create something like that. So the quantum information in a multiple state at one time, we call it as superposition. Superposition. So this is one quantum bit. Now let's say we have 2 quantum bits. So how many states simultaneously that it can have? It can have 0, 0, 0, 1, 1, 0, and 1, 1. So using 2 quantum bits, you have 4 states of information. Now if I have 3, I can have 0, 0, 0, 0, 0, 1, 0, 1, 0, and until 1, 1, 1. How many we have? The classical state that we have using 3 quantum bits. We have 8. So you can see the progress. If we have 1, we have 2 to the power 1. We have 2. If we have 2 quantum bits, we have 2 to the power of 2. We have 4 information. If we have 3, we have 2 to the power 3. We have 8 information. So now if I have 50 qubits, 2 to the power 50, can you approximately guess how much is 2 to the power of 50?
Yes, that's right.
It seems simple, but 2 to the power 50 is equal to the number of suns we have in entire planet Earth. So 2 to the power 50. So if we have 50 quantum bits, if we have 50 quantum information that we can control, it gives you the same analogy with having 2 to the power 50 of classical information we have in classical computers. So it looks easy. It looks amazing. But let's see. So now we can see here. So in normal computer, what we do is when we have an input, like we press A, the computer will process your entry on the keyboard and processing some kind of binary, so you will see the A in your screen. So we can call it like function evaluation. So if you entry your value multiple times, so if you want type 8 letters, you have to type 8 times because each of your state is described with each of your input because your computer can process it classically. It has to process one by one. But in quantum, because we have the power of superposition, so when we have 2 quantum information, so we have the superposition of 0, 0, 0, 1, 1, 0, and 1, 1 at the same time in our hand. So when we use the quantum computers, it will process all of the states together at once. So instead of calculating 4 times like classical computers, our quantum computers can calculate all of the 4 possible combinations at once, at one step. And they calculate everything. It seems good? Seems good. So a lot of people say like quantum computers can evaluate all of the possible solutions at once, and hence quantum computers can solve problems faster than classical computers. Yay, happy! But I'm sorry to disappoint you, but this statement has some degrees of inaccuracy. Unfortunately, this statement has been abused so many times by a lot of quantum scientists to sell quantum computers. Because now the thing is, we can go back to this state. If I have alpha 0 plus beta 1, it is indeed having 0 and 1 at the same time. But the thing is, when you measure, when you observe, when you touch, or like the double slit experiment, you see, try to pick around the quantum particle, it will collapse to the classical states. There is a lot of information here to process. But yeah, so if it's in superposition of 0 and 1, it's not set necessarily in 2 states at the same time. It just gives you the probability that it will be 0 in a probability of alpha square and give you the state of 1 into beta square. So it has some degree of probabilistic. And as you can see, it evaluates everything, but at the end of the day, you just can use one of the information. Yes, it computes everything, but at the end of the day, you can exploit only one solution or one calculation. So that's why here, you cannot use this for all. So quantum computers indeed give you the advantage for some problems, but not all problems. So what type of problems that quantum computers give you the advantage? So you need to evaluate everything. A problem where you need to evaluate every possible thing, every possible combination, but at the end of the day, you just need one of the answer. For example, searching, factoring numbers, and optimization. Searching, let's say you have phone book. So if it's easy, if you try to find the number if you have the name. But my question is, can you find the name if I give you the number using phone code? It's hard. It's hard problem. But for quantum computers, it's easy because it has the capability of evaluating everything. But at the end of the day, I just need one of the answers. I just need to know which name give me this number. So that type of problem. Same thing with factoring. If I give you a big number, like, yeah, very big, and I ask you, can you divide this number? Is it prime or not? So what the computers do, classically, is try every possible combination from 0 to a very big number. Try everything until it finds the answer, is it prime or not? But for quantum computers, it has the advantage because it will try everything. But at the end of the day, you just need one answer. Is it yes or no? It will not give you all the factor that it can give you, like all the factor you need, but it will just give you one answer from all possible combinations. So there is a type of problems that will give you the advantage, but not all problems. So yeah. So what is quantum computer and what is not? It can be a whole topic for discussion. But what I want to tell you is quantum computer is secure, highly parallel, universal, and reversible. There are a lot of properties of quantum computers that are worthwhile to discussion in, like, beside this parallelism property. So yeah, just to give you idea how powerful quantum computer to solve a very specific problem. Here is a quantum computer for factoring. Why we choose factoring number? So factoring number, basically, if I give you 3 and 5 and I multiply together, you get 15. The factoring question is, I give you 15, give me the factor of 15. So the answer will be 3 and 5. It's a very simple question. Multiplication easy, but undoing multiplication is hard. So that's why a lot of our encryption system in our phones basically rely on this very easy problem, but exhaustive. So, for example, our phone is using the RSA encryption, which basically relying on the hardness of factoring numbers. So if I give you number 34579016321, can you factor it now? So it's hard. Multiplication is easy, but undoing the multiplication is hard. So that's why they use this type of problem to encrypt your message. Just multiply it with big number. As long as the eavesdropper or people in the middle doesn't know what is the factor, they cannot break your encryption because it's hard. So for example, if your this is the line of the recommendation from NIST. So in order to be a secure, you need to your numbers, your encryptor, your number to encrypt your message to be 2048 bit length. So 2048 bit length. Because why? Because using the classical algorithm, using a computing performance of 1 gigahertz, so it will take more than 1 billion years to solve. So yeah, if you want to annoy someone, just ask them to undoing multiplication. Probably you will not see them for 1 billion years. So yeah, it's hard for classical computers because the most naive way to solve the undoing multiplication is trying from 1, 2, 3, and then after 3, 5, 7, 11, 13, 17, to try every single combination number until you find a big enough number that can divide those big numbers. So that's the naive way. It takes forever if you get 2048 bits of number. So that's how secure our communication system are, given that we only have classical computers, the key will break in 1 billion years. No worries. But now, if we have Shor algorithm, remember the name Shor? So this guy proposed a quantum algorithms, a quantum computers to factor that can be used to factor numbers, to undoing multiplication. So let's see how fast it can solve our. So given the same number here, 2048 bits. So 1 hertz means our quantum computers do the calculation 1 time at 1 second. So pretty slow. Like it's quantum, so take it easy. So it will break in 1,000 years. So it's okay. So we can increase the speed of quantum computers because classical computers now have like 3.1 gigahertz clock. It means they can do 3.1 billion calculation in a second. So now we have only a quantum computer that has a computing speed of 1 megahertz. So to break all of our encryption system, it takes 1 day. And of course, they can do it better by optimizing the algorithm, make it more efficient. The most efficient of Shor algorithm to break our encryption system will break the 2048 bits of secure number. So to compare 1 billion years of classical computer using quantum computer, it only takes approximately 10 seconds. So now you see the problem. So quantum computer is fast and everything, but at the same time, oh no, it's scary. Like don't invent it. But who knows? Because probably somewhere in the world where they don't publish anything, there is already a quantum computer being built. Who knows? Because everything that we know is from internet. There is also the threat. Actually, like people wonder if actually there are some research people already built a quantum computers without telling anybody. So there is a threat that actually a real quantum computer has been built and now being used. So now we have to tackle this issue. So now we kind of in a weird position, like okay, our classical transistor cannot be shrink further. Okay, make it quantum. Okay, we can make quantum computers. It's so powerful and fast, and now all our communication system in parallel. All of them is in jeopardized. So can we tackle this problem? Yes. I skipped through a lot of things. So now all of our communication system is in jeopardized because it can be break in a second using quantum computers. But turned out quantum communication somehow provide the beautiful solution to face the problem that being provided by the quantum computers. So it's kind of beautiful, like you fight fire with fire. So you can exploiting quantum phenomenon to establish secure key sharing. So we have the same properties: entanglement, measurement, collapse, superposition, and no cloning theorem. So now let me take to the classical communication first. So we can create absolute secure communication classically, but it is impractical. Like how? So every time before we transmit message, we need to exchange secret key. But it is impractical. Like how you can trust? Because you need to share your key privately, securely, but you have to do it multiple times in a channel that you don't know is it secure or not. The most practical way is like you meet in person, exchange the key, and then separate again, send your message. If you want to send another message, meet in person, exchange the key, and then separate, send the message. Classically, it's absolutely secure. Nobody can break that. If your message between you two is privately exchanged privately, but this is impractical in this world. If you want to send message between Europe and America, how do you expect to exchange the key privately multiple times? So basically quantum, so yeah, this is the multiplication is easy. So this is the example. Because this is impractical, so we use the method that we call as public key. So we can publish our key to public, like, have this number, solve it if you want, you will not break it. So it's a problem like this, A times B, this number, find A, B, and given that A and B are prime numbers. It's hard. This is tackle the problem with exchanging key like multiple times. You can have this key announced publicly, and then if your message A and your friend is P, it's easy. You just publish it and nobody knows. So this is the number, if someone wondering. It's real number. So quantum key distribution. So now we have a problem to tackle. So in order to handle the problem that all of our communication system can be break by quantum computers, we necessarily need the one-time path solution. The only way to provide secure communication now is the one-time path solution. You cannot announce the old method. You cannot announce the public key anymore, because in seconds your key will be break by quantum computers. So now we have to back to square one to the one-time path. But how we do it classically, it's impractical, but turned out quantum properties provide you that you can do one-time path, but assisted by quantum channel. So it will look like this. So you have classical communication channel where you exchange your message, but your key is exchanging to quantum channel. And it will be repeated several times. Because now, in order to exchange one-time path, you don't have to be at the same place to exchange the key. You can do it remotely as long as you have quantum channel. Do you want me to explain how the one-time path works? So, let me try. So now, let's use photon. Like, photon can be, like, anyone can see me? Because I'm a bit tiny in size. So, photon can be in, let's say this is vertical polarization and then horizontal polarization. So, let's label this 0 and 1. But at the same time, you can have the right polarization, and also left polarization. Let's label this 0 and 1. Now the thing is, if you send this state, the vertical polarization, but your receiver give you, like you detect in this basis, what you will have in your receiver is 50% of getting this or 50% getting this. So it will be random. But if you send this, the vertical polarization, but you detect this using the plus detector, you will always have the 1 in 100% probability and 0 in this. So they use this kind of randomness, but also the absolute measurement here. As long as Alice and Bob measure in the same basis, they will always have the same value. But now you can see what Alice and Bob exchange is not the key. They can just tell anyone the basis they use to measure. Because if Alice measure in plus and Bob always measure in plus, they will always have the same value. But if someone in the middle try to listen, what they listen is actually just the basis. They only listen like man in the middle, if he or she tries to listen, what he or she knows is the basis. Is it the X or the plus? But they don't have any idea, is it 0 or 1? They only know the basis. But if Alice and Bob exchanging the measurement basis and they discard all the different bases, they will exactly know which one is they measured, like what is the secret key, because they will always have the same answer. So you can repeat this all the time, every time, no matter how hard you listen to the key exchange, you will never know what is they exchanging, what is the secret key. Because as the listener, because what they actually exchange is only the information about the basis. Is it plus or X? But Alice and Bob each know, if I measure X, Bob also measure X, and we will have the same value. Is it 0 and 1? It's secret just for Alice and Bob. So it's so secure. So yeah, it's called E91 protocol. They have BB84, they have B92, they got so many protocols. So yeah, that's quantum communication. So one aspect in quantum communication, also quantum teleportation. It sounds impressive, but not that impressive, but it is impressive, so confused. So what actually quantum teleportation? So if I ask all of you about teleportation, what you have in mind? Like I'm disappearing here and then appearing here. So yeah. So what quantum teleportation is near that experience, but what they exchange is quantum states. So you remember that the quantum states can be alpha 00 plus beta 11 plus gamma 10 and all those possible combination. You can discard those information and then send it to your respective respective friend and then recover that alpha 00 plus beta 11 and everything perfectly. So here, so what the actual quantum teleportation exchange to replace is the quantum states, not physical states. So sorry to disappoint you, but this is impressive. Like, why people need quantum teleportation? First, it's hard to actually send directly the superposition through the channel. Let's say you have alpha 00 plus beta 11, all those type of superposition, but your quantum computer is using superconducting qubit. It means you need to freeze all of your communication channel in 0 degree temperature. It's not practical. It's just weird if you step on the street and then you froze immediately because you step on a quantum channel that you freeze in absolute 0 temperature. So teleportation basically saying that you can transport quantum states by cause of classical communication, classical bit 0110, and also entangled qubit. And we can destroy the quantum state in this place, sending the bit, classical bit 0101, and then the people on the other side can recover perfectly what you have in this side. So quantum teleportation. So, in terms of quantum communication, how far people have reached. So, for example, here record distance for quantum cryptography, it's from Cambridge, I think, and Toshiba and PT. So they successfully create a 421 kilometers quantum key distribution network. So now, if people say quantum cryptography, it's basically the same thing with quantum key distribution. It's just way people try to close over thing. And then US National Lab team up built a quantum network. China Sunlight used quantum cryptography. China quantum satellite achieves spooky action and a record distance. Quantum satellites demonstrated teleportation and encryption. So my point is, you don't have to understand the technical details, but what I want to try to say is, even though the quantum computers will exist sometimes in the future, that may jeopardize all of our classical communication, the secrecy of all our communication system, we still can achieve absolute secrecy using quantum communication. So it's a deal that you have to have both. It's not an option that I just won't have quantum computers without quantum communication. No, you cannot, because if you don't have quantum communication, all of your classical communication basically is in jeopardy. So you need to build the quantum communication to ensure that it's still secure, even though in the future we will have quantum computers. It's like quantum computation is secure even though we have quantum computers. It's definitely more secure even though the quantum computers never arrive. Because classical computers cannot crack it. If quantum computers cannot crack it, how classical computers can crack it? So yeah. So basically, if a quantum internet is basically, yes, quantum computers plus quantum communication. It's just interconnected. But the thing is, I don't see in the future that we will have like a quantum computers on, probably like on top of my desk. Let's come back to the like 1968 when people try to create quantum like computer networks. I don't think people will imagine that the size of computer will be so small that everyone have it in their pocket. Nobody has the imagination that time, like what can the computers can and cannot do that time. So now we are reaching the point where can we have a quantum computers on top of our desk in the future, like actual quantum computers that can perform a lot of things faster than classical computers, can provide you a very secure communication system, and so on. So why quantum internet? So it basically gives you the advantage of quantum computers, it gives you the advantage of quantum communication systems, it gives you the advantage of combining them, because exploiting the advantage of having multiple quantum computers in the quantum network, you can chunk your information smaller and then like sharing the load between the several nodes of quantum computers in the network. Also, the recent finding, it's the most interesting part, is doing private quantum computation. Because quantum itself is very secure in its own, like inherently secure. Basically, you can perform a computation. So let's say you have quantum computers in the server. It is possible to delegate problem to a quantum server to be solved privately. It means the server itself has no idea what the quantum computer tries to solve. So now, like if we store something in the cloud, there is a huge change that the owner of the server knows what you save on the cloud, what you try to process. Or if you do some kind of calculation in the server, most of the time the server will know what you try to calculate, what you try to demonstrate, or anything. But in quantum internet, this is interesting enough. You can send quantum computation task in the quantum server, in quantum computers, without revealing what is actually you're doing in the quantum servers. Well, the quantum server will know the number of like resources you take, but somehow it doesn't know what you do with the quantum computers. Because once the server tries to take a look what you're trying to do, the whole system will collapse to the classical states. And the person who sent the computation task at the first place say like, it's collapsed. Are you trying to like take a look at my computation? And then I'm no longer trusting you. So there is edge that interesting here, that you can get an absolute secrecy in your computation, in your internet in the future. So it's easy, right? So this is like the level that we try to build. So this is step by step. Like first we in order to build like on top of it, like the the ultimate quantum internet. But before that, we need trusted repeater, we need prepare and measure, we need entanglement generation, we need quantum memory, we need few qubit filtering, and quantum computing before we finally reach the so-called quantum internet. So you can see there is many steps before we can reach the thing called quantum internet. So what is our current situation? So this is quantum computers that exist today. The number is less than 100 qubits. If you remember this figure, here actually say if you want to make a quantum advantage, you need 2L square logical qubits. In here, L is the length of real problem, 2048. So if you plug in the number, at least you need 8 million of qubits in order to achieve quantum supremacy. But now the current stage is we have 100 qubits. So from 100 to 8 million qubits, 2 years. So yeah, so this is our system today. And here, the SHAR algorithm, sorry, this one, the blue with the net. So this is basically what we need in order to achieve quantum supremacy. And now we are here. So in terms of number of qubit, we need millions, and we need gap error probability lower than 10 to the minus 5. So you can see it's a small step. Now we So, how good is good enough? Because here there is a problem that you know that quantum particle is so small. Any environmental impairment is basically will disturb the states. So it is impossible to create a absolutely perfect quantum gate. Because for example, heat is basically electron moving. So when you have an electron moving, basically your qubit is moving. Like you, in order to achieve a perfect qubit, you have to have the capability of saying to electron, stay quiet, don't move. So you be like the perfect qubit. Or say to photon like stop there, don't move. That's the perfect photon with 100% accuracy. We cannot do that. Because electron is the environment itself. Photon is the environment itself. Heat what we have is the electron moving. So noise, it's our part, our life. So let's see here. Let's say we want to do like the easiest task of 100 bits number. So what we have here is 100 times 100 and times 2, we have 20,000. Let's say each of our qubits here, error in 10 to minus 3, it's pretty low, 0.10%. You have 1%, one time of error every 1,000 times of try. But if you try to put on the number 0.999, so in order this process to completely perfect in the first step, you need to everything to be perfect, given at the same time. So it can be translated as 0.999 to the power of 20,000. If you think 0.999 is good number, when you try to power it with 20,000, what you get is this, 2 times 10 to the minus 9. So basically, your success probability, given that your component behave this way, is just almost 0. So is there any way around it? Yes. So basically that's my research, but I will not tell anything about my research. My research is basically try to solve this problem. Like you want to build up quantum computers, but all of your qubits, all of your gates are faulty. Like how can we cope with that? How can we build computers that each of the components is faulty? So yeah, that's my research, and I will not talk about it. But yeah, just I want to summarize. So yes, it's indeed a lot of to take, I admit. So in summary, what is quantum internet? Basically, it's quantum computers and quantum communications combined. So we will have the advantage of quantum computers, the advantage of quantum communications, and then they will be combined. Are we there yet? Yes. Oh no.
Yes, and
So are we ready to go quantum? The correct answer is yeah and no. Theoretically it works, but let's see if it works. Okay, thank you very much.